Mm, all right. Okay, so hello and welcome everyone. Welcome to this lecture. So last time, so there was some hiccup last time. I mean, we tried to work with. So there was some network issue from my side, and unfortunately, there was some network. The network was down in my campus, so I was not able to take the class in full fledged. So I will recap what I was trying to tell back then, uh, because I think maybe that part of the lecture was not clear. So I will recap that, and then we will move forward and proceed. Okay. So last time we had started with some basics of information theory, right? So first question that we asked ourselves was, okay, what do we even mean by the word information, right? So so basically, information, we saw that information is nothing but anything that reduces uncertainty can be called as information. So for example, let's say if you have a coin, right, and both of its side is heads, okay, and so I mean, I toss a coin and I say that, okay, I ask you, so you are basically, let's say, guessing something. I toss this coin, and even if I don't show you the output what I have got, you can tell that there is a heads that I have that I must have found. So in some sense there was no uncertainty here, right? So if there is no uncertainty, then I cannot reduce the uncertainty, and hence there is no information, right? So this was
Yes.
so like sorry, was there something?
Yes, yes. Yeah. Yeah, I was saying that I understood you.
Okay, sorry. So the idea was, so yeah, so the basically, if everything is known to me, there is no uncertainty, and hence if there is no uncertainty, I cannot reduce the uncertainty, and hence there is no information that is present. So in this case there is no information, right? The next thing that we saw was, then changed the situation, and I said that, okay, let's say there are two outputs, heads and tails, and I get heads with zero point 0.9 probability and tails with zero point 0.1 probability. So now you can see that, okay, now there is some uncertainty, right? Because now I cannot be 100% sure that, okay, the output is going to be heads or the output is going to be tails. We don't know that. So right. So I mean, I hope you can see that if I provide you something like, if I provide you some information such as, the probability of heads is, let's say, zero point 0.9, I am giving you some information, I am conveying you some information, using which you can, make some predictions, or design some model or things like that. So so basically, any random system or any uncertain system has some information perspective to it, okay? So we have seen that whenever we are dealing with random systems or random experiments, the tool that we use is going to be probability theory. We had recapped probability theory in the first two lectures, right? Okay. So basically what we will be doing is, we will be using probability theory as a tool to study these random systems, and what do we exactly mean by information, and how much information does a system contain, and things like that. And that will basically, pave our way for machine learning, because machine learning is also, working under uncertainties in some sense, and hence the most information that we can gather, the more information that we can gather, the better it is for us. Okay. So uh, so then we saw what entropy is, okay? So if we remember, in our 11 12 days, I remember that in thermodynamics, we used to study entropy, and we were told that, okay, entropy of a system is basically the amount of randomness that is there in the system, okay? So I mean, at that time it was just a formula for me, something related to pressure, temperature, and things like that. I don't remember, but I mean, that was a good intuition though. Okay. So today, even today, when I have to think of entropy, that is the first thing that clicks my mind. Okay, there is some randomness that is going to be quantified. So entropy, in some sense, I mean, not this is not completely true, but nonetheless, it gives you a sense of, how much randomness is there in the system. Okay. So the way to define is as follows. So suppose x is a discrete valued, random variable over a discrete support. Okay. So the probability of a certain element x is p of x. So p of x is the probability that the random variable x takes the value small x. Okay. And the entropy is basically quantified by by this formula that is given here. Okay. So this is like negative summation of, so this is negative summation of p of x log p of x, right? And the sum is over all the x's, small x's that belong to the support. Okay, all small x's that belong to the support of this random variable x. So this itself is a weird looking formula. I mean, why should this even quantify entropy or randomness in a system, is the first thing that should click your mind. Like, does this formula even make sense? Or I mean, I don't know how, like, why should I even consider this formula? I can take any formula, right? So the why part, okay, is something that has an answer, right? But if I start deriving how this formula comes, it will be very tangential to our main objective, which is to go till MLE today. And hence, what I will instead do is I will give some justification. Okay, I will in some sense justify why this formula is good, and why should we use it, maybe. Okay. So what saw after that was, okay, we saw that, okay, we took an example of a fair coin. Okay. So a fair coin basically has, let's say, two output, heads and tails. Okay. And each of them are equally likely, meaning that each of them occur with probability 1 by 2. So so in some sense you can see, right, that there is absolute randomness, because this coin doesn't favor either heads, it doesn't favor the tails either. So I hope you can see that it's very random in some sense, because you cannot. So 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 if I even, like, heads and tails are not, since none of them are favored, your guess is going to be a random guess. Okay, I mean, you randomly choose something and tell me that will work better than doing any calculation, because it is a fair coin. That is why we call it fair, right? Because it doesn't favor any of the outputs. So okay, so we saw that, okay, we saw what we tried to calculate the entropy of this fair coin, and the entropy formula is this one. So we simply substituted, so there are two possible outputs, heads and tails. Okay, for heads the probability is 1 by 2. So 1 by 2 log of 1 by 2, right? This is for heads part. Okay, and then we added the tails part. So half is the probability of tails. So half log half will be the corresponding term for tails, and this is for basically the tails part. And a simple calculation will tell you that this is nothing but equal to 1. So h of x, so okay, so we will denote entropy by h. Okay, in general the entropy is denoted by h. So we saw that, okay, entropy of this system is 1. Okay. So we did this, and so basically, in some sense, it is saying that the amount of randomness in this system is 1. Okay. Well, now you will ask me that, okay, you did this calculation, but why should I believe you? I can, like, how can you justify this one? So what I will say is that, okay, so this was for a fair coin. Okay, let us take a biased coin now. So I hope you will agree that a biased coin has more information in it. I mean, it has less randomness. Why is it so? Because let's say you have again a coin, but this time the probability of heads is 3 by 4 and the probability of tails is 1 by 4. Okay. Now, well, now you can see, right, that there is this coin favors heads more than it favors tails. Okay, so the probability of heads coming up is more. So in some sense, you are more certain, right? In some sense, you have reduced your uncertainty. This system, this biased coin system, has reduced your uncertainty, and hence there is more information, and hence you will, hence there is less randomness, and hence you should expect that the entropy should be, less. So we did again the same calculation. So this time the probability of heads was 3 by 4. So 3 by 4 log 3 by 4 will be the first term for heads. Okay, and then the term for the tails was 1 by 4. 1 by 4 log 1 by 4 will be the term for tails.
Hello,
Okay.
Piyush.
Yeah, yeah.
Hello. Yeah, Piyush, is there something wrong with the link of the meeting? Like, have
uh
you done something? Because Namanba is
mhm.
not being able to join. It shows that the meeting ID is wrong or something like that.
Oh, okay, is it okay? So let me see that. Okay, okay, so just a second, how should I do it? Okay, so there is a let me go in my calendars and check. Okay, okay, so this is the link. So let me copy it. So Jaisal, maybe I am forwarding this link to you. I mean, I hope that this is the same link. I have
Okay.
forwarded it to you on WhatsApp. Uh, just let me know if it works because I haven't changed anything. Okay.
Okay.
Okay. So wait a second. I have shared the correct link, right? So let me just check once. Come on, V. Yeah, I have shared the correct link. Right. Yeah.
Also, Piyush, maybe there is something wrong with your screen too, because some of them are not able to see your screen.
Uh, okay. You are not able to see my screen. Okay. So let
Yeah.
me
Because I
stop
am
it.
able to see your screen, not others
All
are
right.
not able to see your
So
screen.
let me reshare it. I have unshared it. Okay. I am resharing it. So maybe now you can tell me that if it is visible or not.
Yeah, now it is visible.
Okay.
Yeah,
So
now it is
can
visible.
someone else, tell me if it is visible or not? Because uh,
It's
maybe
visible
you
now.
are. It's visible now. Okay. So
Okay.
what part did you miss? I don't know. What, were
I
you
was
asking
unable
to?
to watch everything. I didn't see your screen. Your screen wasn't shared with me.
Okay. So, okay, so this is anyway getting recorded. Okay. So maybe what I will do is I will recap it. So, okay. I won't like go in depth, but I will just tell what we did till now, and maybe we can continue from there. So I don't know why this has happened, but okay, let's see. You can ask any question if you have any doubt. If you didn't understand anything, let me know. Okay. Yeah. So Jaisal, is the link working now? I don't know. Has anyone tried to join it?
No, actually, there is some problem. Still, there is still some problem, but I think it is from their side now, so they'll be able to resolve it, or they'll watch the recorded lecture.
Okay. So I
So
don't
no
know.
worries,
Do
you
you have
continue. No, you continue. They'll watch the recorded lecture because like we cannot waste any more time. So.
Yeah. Okay. Okay. So maybe I will just for those who were not able to watch the screen, I will just again, repeat this thing. Okay. So the idea was that we defined a formula for, we came up with a formula for entropy, and this was the formula. And we said, we asked ourselves, okay, why should this formula, work? Okay. Why should this in any sense quantify the amount of randomness in a system? So for that, what we did was, okay, we considered a fair coin. So the fair coin favors no fares no output. Okay, so the probability of heads and tails are exactly equal, and hence it's like a it's the most random coin that you can come up with. Okay. So and then we substituted these probabilities in this formula for entropy here, and we saw after some calculation that okay, the amount of entropy that this formula tells me is actually equal to 1. And so yeah, so we came to the conclusion that okay, the entropy of a fair coin is actually equal to 1. But then you can ask me that okay, you told me that entropy of this of this coin is 1, but how? So like why should I why should it make sense? Because I can come up with any number and tell you that okay, this is my entropy. Any formula basically will give you some number, and I can quantify that as entropy. So what is so what it doesn't tell you anything. It doesn't justify how why is this formula special. So I said that okay, let us now consider a biased coin. Okay, I hope you will. So in a biased coin, the idea is that the probability of heads is something and probability of tails is something, but they are not equal. So in this case, the probability of heads is 3 by 4 and the probability of tails is 1 by 4. And which means that heads is more likely to come as compared to tails. Okay. So I hope that you will agree that, I mean, if I tell you this information, right? I tell you that okay, heads is the probability of heads is 3 by 4 and probability of tails is 1 by 4. And I toss the coin. You will bet that okay, the output is heads. Why? Simply because that there are more chances that the output is going to be heads. That's all, right? So it's so in some sense I have given you some information, right? Meaning that you are more certain that the output is going to be heads as compared to tails. Does that make sense, Nikunj?
Yes.
Okay. So but this is just an intuition. Okay, so to formally prove my point, I substituted these values in the formula of entropy, and this is nothing but the substitution of these probabilities in the formula. And we did some calculation. So the calculation involves log and all those things, so you need a calculator, and I did those things, and it came out that the probability, so the entropy of this biased coin is now 0.65, right? So so okay, now you can
So
see,
like,
right, that yeah.
the entropy specifies that how likely the results, how li- uh,
No, no,
how
no, no.
trustworthy the results should be, right?
So entropy tells you how much randomness is there in the system.
Yeah, that is what I'm saying. The lower the entropy, the more the
Yeah,
trustworthy.
certainty.
Yeah,
Yeah,
the most more certain the system will be, right?
right. So as you can see, right, the entropy for a fair coin was 1, and the entropy for a biased coin is 0.65. So since so you can see now you can see, right, that a more random system, the most random system had a high entropy, and a more certain system had a lesser entropy. So I mean, this is not a formal justification, but nonetheless it is a argument that proves my point that okay, entropy actually helps conveys or quantifies that how much random a system is. Okay. So this was my point, and I think around this time, everything went southwards, and I lost my connections, and we had to abandon the lecture. Okay, so let us continue from here. Okay, so okay, so let us now. So let us take. So let me just put up some formula. Okay, it is not even a formula. It is just a substitution, but it comes in handy. So I will just write it. So consider a random variable which has two outputs, or as we call it, it is a binary random variable. Okay, x, which has two outputs, two possible outputs, 0, 1, and 0. Okay, the probability of 1 is, so WP means with probability. Okay, with probability P, 1 occurs with probability P, and 0 occurs with probability 1 minus P. I mean, if I give you that the probability of 1 is p, then you can automatically come up with 1 minus p, because the sum should be 1. Okay, the sum of probability should be 1. So this is the follow. So this is a binary random variable. So it is also called, Ba- Bernoulli. I mean, I had discussed this in probability theory part, but it's a Bernoulli random variable with parameter p is what it is called. Okay. But even if you don't remember it, it's fine, because most of the time you won't remember the exact distribution. Okay, so this is the binary random variable. So the what is the entropy of a binary random variable? It's a simple exercise. You can see, right, that minus p minus. So this, it is a negative sum of p. So I mean, if I have to, just this one I will write it elaborately, but after that I won't. Probability of 1. So probability of x equal to 1 log of probability of x equal to 1 plus probability of x equal to 0 log probability of x equal to 0, which is negative. So probability of 1 was p log p plus 1 minus p log 1 minus p. Okay. So I mean, if I take this inside, this negative side inside, I can write this as p log 1 by p minus, plus 1 minus p log 1 over 1 minus p. Right, so this is generally what people call as h of p. So this is nothing special. Okay, I mean, it is just a, it is just something that keeps popping uh, here and there in information theory. So people have given this thing a special name, and they call it entropy of a Bernoulli random variable with parameter p. But even if you don't remember it, I just wrote it down, but even if you don't remember it, it's fine. It's like, just remember what it is. So you can calculate it anyways. It's nothing special. Okay, so now I think we have covered this thing. Okay, let us see some few more definitions. So another thing is, what is your joint entropy? Okay, so we saw what an entropy is. The joint entropy is nothing. I mean, entropy was defined for a single random variable x, right? Joint entropy defines the entropy of a system which has two variables. Okay, a pair of discrete uh, uh, random variables. So if it is denoted by h of x comma y. Okay, so this is the like notation, h x comma y. So it is joint entropy of a pair of random variables x comma y. I mean, since they are a pair of random variables with joint distribution, p of x comma y is given by. So the formula is very similar to that of entropy, but it is just for the sake of completeness I am writing it. So there are two summations because there are two random variable. One is over x and another is over y. Okay, and instead of p of x you have p of x comma y log p of x comma y. So so I hope that you can see that there is nothing special, right, in this formula. Earlier you had one summation, this was not there. There you had only one summation, and you only had one variable, so it was just p of x, and inside the log also you had one variable. So it's just that since you have a new you have a pair of random variables, there are two summations, there is a joint distribution instead of marginal distribution. Okay, so I mean, all right. So this is, I think, this is very clear. Okay, so similar to joint entropy, you have conditional entropy. uh, conditional conditional entropy. Okay, let me just add a new page. Yeah. So again, let's say, x comma y are a pair of random variable with joint distribution p of x comma y. Okay, p of x comma y. The conditional entropy, the conditional entropy is defined as defined as so I hope you remember something that we saw in probability theory, which was conditional probability, which was p of y given x, right? And this was, how was it defined? It was defined as uh, p of x comma y upon p of x. I hope you remember this formula. This is something that we had seen in, probability theory itself. Okay. Now, similar to that, we have something called conditional entropy. Okay. And what is a conditional entropy? So the conditional entropy is given by this formula. So it is denoted by h of y given x. Okay. Right. So it's similar, the notation is similar to that of conditional probability, and it is defined as this is equal to, so this is defined as when, so if I just write equal to sign, it means that there is an equality. If I add a triangle over it, it means that I am defining something. This is a new notation. So the, what is this equal to? So the, it is equal to, it is a sum, it is a single sum. Okay, it is unlike joint distribution, is joint entropy, it is a single summation. However, the single summation is over the variable that is that is conditioned here. Okay, so in this case the conditioning variable is x, so the sum here will be over x. Okay, and whatever the sum is over, you write that probability here, so p of x. However, this now, this is something
Hello,
that will,
Piyush.
look. Yeah, yeah.
So I don't understand the sign that is equal to a triangle. Like, so what is that?
Okay, right, right. So let me write it down here. Okay, so I hope if I write, something like 2 is equal to 2,
Yeah.
this means that there is an exact equality. Okay, okay,
Okay.
right. So, and if I write a
Yeah, yeah.
is equal to 2, if I write a is equal to 2, it means that a is some placeholder, and I am assigning the value of 2 to it, right?
Yes.
So this is what equality means. However, if I write a something like this, okay, I
Hmm.
add a triangle over it. So what this means is that, this means that I am defining a. Okay, so a is defined to be 2. There is a difference between these two. So don't think of it as equality. Think of it like a is some quantity. Okay, and it is defined to be 2. uh, I don't
So
know.
it does not need to be true. It has to be true, right?
Yeah, yeah, yeah,
Like,
it
yeah.
has to be.
Okay.
Okay,
Yeah.
right. So with that, yeah, so I was explaining the formula for conditional entropy. The idea is that whatever the conditioning variable is, in this case x, take the summation over it, take the density or distribution of that. Okay, and then take uh, the conditional entropy. So this is, okay, let me just write it first. Okay, so this is something that is new to us. Okay, till now, what we have seen is that there is some entropy term here, and there used to be a log term here, and log of some probabilities and things like that. Now you will ask me, okay, like how does this make sense? Here is a conditional entropy, and here it is again a conditional entropy, right? But notice that there is a difference in the way I have written it. Here I have just written the conditional variable x, whereas here I have written the what the conditional variable. So So there, I hope there you understand the difference, right? If I tell that y is conditioned on x, I don't tell you what the exact value of x is. It is, there is some uncertainty about x as well. Okay. However, if I tell you exactly what the value of x is, then I hope you can see that it is, you are certain about the value of x. That is the difference in these two terms, the h, the entropy term here and the entropy term here. So basically what I mean is, let me just write it down and then maybe it will be more clear. So there is this summation over x, okay? P of x is there. Let me write down what this term means, okay? This term here means, okay, this is another summation over y, and it is p of y given x. So now you will see something that you always, that you have known, okay? So this is negative log of y given x. So maybe now you are, maybe I should have I should have defined this first and then I should have defined this, but nonetheless let me try. Okay, so this term, that this notation here means that, okay, if x capital, the random variable x takes the value small x, what will be the entropy of y? Okay, so there is a system which has two variables x and y. Sorry, let me denote it by capital letters. X and capital Y are two random variables. Let's say, pressure and temperature, something like that. And then I tell you that, okay, there is some conditioning between these two, so y is dependent on x in some sense. But I tell you that, okay, the exact value that x, capital X takes, is small x. Okay, and then I ask you that, okay, there were two random variable x and y, I have told you the value of x, capital X, which is small x. Okay, now tell me what the entropy of y is, or in other sense, what is the randomness in y now? This is the question that I am asking. So this term denotes exactly that. It is the randomness in y, given that the value of the value of random variable x is small x. So the way it is defined is, you take the conditional probability of py given x and basically calculate the entropy of it. So py given x log py given x, and sum it over all the y's. Okay, so this will be for a one x, one small x, right? I hope you can see that for one small x, this is the value. Okay, now what I am asking you is that, okay, take all such small x's, calculate all their entropy, all the conditional entropy, or I mean this thing, whatever this entropy is, and then multiply them with the corresponding probability of x and sum them all. So am I making sense, or is it not clear maybe?
Yes, 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 we get.
Right? So
Yeah.
this is what this means. Okay, now if I have to simplify what this term is, right, so I can take this negative sign outside. This will be a negative sign that will come here, and I can take, combine the two sums. Okay, this, so there are two sums. This is the first sum, this is the second term sum. I can, club them. So one sum is over x, another sum is over y, and it will become p of x, p of y given x, okay, log of p y given x. Okay, so if I further simplify it, this is nothing but these are two summations x and y. So now you should be able to see this thing, right? P of x, py given x, this is what, this is nothing but, joint distribution, p of x comma y log p of y given x. Okay, so I hope you can see that this is the formula for, I mean, the conditional entropy essentially boils down to this formula. I hope, I mean, you can now appreciate that why we didn't write it as something like, py given x, log py given x, because this would not have made any sense, because uh, think about it, right? There are several values that x can take. How do I accommodate that, right? So if I take only one value of x, I am not I'm not considering all the randomness that is there in X. So that is why this kind of definition is required. Okay. So moving forward, so this was the idea of joint and conditional entropy. Okay. Now, um, so let me give you a homework. Maybe I won't prove this, but this is rather a useful thing to know. So we saw what a joint entropy is. Okay. We also saw what individual entropy is. Like if I just give you the random variable x, what its entropy is going to be. And now, just now we have defined what the conditional entropy is, right? So a natural question to ask is that is there some relationship between these three quantities? So the answer is yes, there is some relation, and the relation is as follows, right? So the sum of the condition, the margin, so the sum of marginal entropy or the normal entropy and the conditional entropy gives you the joint entropy. So I am giving you this as maybe you can try it. While doing some, you can just try and see how this comes out. Just write down the formula for this, or maybe try to simplify the RHS first and see if it is equal to the LHS. That is a better way to do it. But nonetheless, let me tell you something. Okay, so I hope you remember from our probability theory class that the joint distribution can be written as multiplication of the marginal distribution and the conditional distribution. This was what this was Bayes rule. Bayes. Okay.
Yes, yes.
so I so if I just take log of this, right, log of p of x comma y, this will become log of p of x plus log of p of y given x, y given x. So now see, there is log of joint distribution. Okay. So there is log of marginal distribution, and then there is log of conditional distribution. Okay. Now let us see here. This is entropy of joint distribution. It is entropy of marginal distribution, and this is entropy, conditional entropy, right? So there is some sort of relation. My point is the following, right? Entropy behaves like log of the probabilities. I mean, don't quote me on this. Like this is not completely true, but you will see at many places, right? The behavior of entropy is similar to that when you take log of the probabilities. It is just an observation, and why this happens is because the because of the formula of entropy has a log term in it. I mean, it also has a probability term in it, but the log term, somehow dictates how these entropies behave. Okay. So this is just an intuition. There is nothing formal here. Okay. You need to formally prove that how this term, is actually equal to this term. But nonetheless, I wanted to give you some intuition that, okay, it is, it is not that, complicated. It is just it behaves similar to log of the probabilities. That's all. Uh, okay, so having said this, okay, so there is a special name to this formula. So this formula, this thing, this homework is called chain rule. Okay, chain rule. So I hope you can see why it is called chain rule. You had joint two variables. You decomposed it into a chain of like x, y given x, and similar to things like that. So in general, if you have like n random variables, right, you have h of x1, x2 till like xn, you can actually write it as follows, right? You can write it as h of x1, the first random variable, plus h of x2 given x1 plus h of x3 given x2 comma x1 plus h of x4 given x3 x2 x1 till we will go till h of xn given x n minus 1 to x1. So this is the general chain rule. If you substitute n to be 2, this is what you will get. Okay. So again, I mean, this seems like a very big formula, this whole thing. But nonetheless, if you look again, think of Bayes rule. What was Bayes rule? P of x1, x2 till xn was P of x1, similar to this, but just multiplied. X2 given x1, P of x3 given x2 comma x1 till multiplication still P of xn given x1 to xn minus 1 n minus 1. And if you take log on both sides, right, I mean, you I hope if you take the log on both sides, you will get something similar. All these multiplications will become additions. You will get addition here, things like that. And I mean, as I was telling you earlier, the behavior of entropy is something similar to that of log of probability. Okay. So is it clear till here? So I don't know. Was I clear, or was it too heavy, or do you have some doubts? Maybe this is a good time to ask. Any questions?
No,
Okay.
no, yeah, we get it. Yeah.
Okay. Thanks. Okay. So this is done. Uh, okay. From this, actually, you can also see this the following, right? So there are many things that you can now derive. Like, just now I told you that h of x comma y is equal to h of x plus h of y given x, right? But now you can see that, okay, what is there so special about x? Why should x come here and why should y come here? Since I have assumed nothing about x and y, why should I give preference to x, and why should it be like this? I can also write this as h of y plus h of x given y. I mean, because there is no special thing about x comma y pair. I mean, the ordering doesn't matter. So I can write it as I mean, it is up to me how want to write it. So from this you can see, right, that these two quantities are also equal. And if you like kind of rearrange these two, what you will get is h of x minus h of x given y is equal to h of y minus h of y given x, something like this. So I mean, I don't know. So it's like the following, right? That amount of uncertainty in x. So let's say there is some uncertainty in x, okay? And if I provide you the information about y, this is the uncertainty, and I subtract them, okay? And this information or this uncertainty is equal to the amount of uncertainty about y minus the amount of uncertainty in y when I provide the information about x. That's all. Okay. So I mean, you can prove several things like this once you know the definitions and things like that. Okay, so let me come to something that is very important now. Okay, and in machine learning as well, we will see this thing that keeps coming on. Okay, so what is that thing? Let me change some colors. Mm, like this. So that is the concept of relative entropy. Okay. So what is relative entropy? This is something which is important, okay? Like this will you will if you go in machine learning, this is something, or perhaps maybe theoretical ML or in ML in general, this is something that will keep popping on, okay? So let me like formally do this, okay? So the relative entropy is a quantity again, okay? Uh, uh, okay. Okay, so it is denoted by D, okay? D P Q. This is the notation, okay? This is just a notation. This is the relative entropy between in distributions P and Q. Okay, so let me define how it is defined. This is also known as Kullback Kullback Leibler Kullback-Leibler uh, distance, or maybe distance is not a correct word, divergence, or in short it is known as KL divergence. So have you heard of this term KL divergence? Like it keeps popping on nowadays in ML. Have you come across it or anything like that? I don't know. If you are maybe active in ML, then KL divergence is something that keeps coming in, and we kind of use it in our everyday life and research. So let me nonetheless define what it is. So dpq, okay, is equal to, this is nothing but summation over x. Okay, so x is some random variable. So p of x log p of x by q of x. Okay, so what does this mean? Okay, what does this weird looking definition even mean? Let me give you some sort of maybe intuition, or let me first explain what this is. So let us suppose that x is a random variable, okay, and it takes only two values, 0 and 1. Okay, let me copy this thing and paste it below. Okay, and let us say that there is some. So let assume, you can think of 0 as tails and 1 as heads. Okay, like there is nothing special. So tails or heads, you can think about it like this. Or in other case, in other sense, think of them as you have two coins. Okay, now the first coin, okay, the first coin assigns a probability of half and half to both of them. Okay, and there is another coin which assigns a probability of 1 by 4 to tails, and probability of 3 by 4 to heads. Okay, so so I have two coins. For the first coin assigns a probability of half and half to heads and tails. There is another coin which assigns probability of half 1 by 4 and 3 by 4 to tails and heads, okay, respectively. Now so what people thought was, okay, is there some sense of is there any, can we come up with a sense of say distance between these two distributions? I hope you will agree that these are two distributions. Can we come up with some notion of distance between these two? Okay, and that distance is characterized by this formula, this formula that I have written. So the one thing that you will ask is, okay, why should I trust you? Well, the answer is, again, I can, the like similar to entropy, I cannot give you exactly the exact derivation of this because that will be tangential. But nonetheless, let us think of some examples. So so KL divergence in some sense tells you how much these two distributions P and Q are far from each other. Okay, so let us take some example and like maybe justify it. So let us say P is half comma half. Okay, so it is half comma half. Okay, and Q is also half comma half. So both the distributions are the same. So what does the value of KL divergence would be in this case? This will be summation over, so let me write it. So that will be half. So since P and Q are the same, P by Q will be 1. I hope you will agree with that. This thing plus again
Yes.
half log 1, right? And we know that log 1 is nothing but this is 0, this is 0,
Zero.
right? So this will become what? 0.
Divergence will be 0.
Yeah, so this is telling you that P and Q are very close, the distance or time. So right now let me call it distance, but it is, there is some there is a asterisk there, but let me call it distance. So P and Q are basically very close to each other is what this is saying. It is actually the same in this case. However, now let us take some other example. Okay, so P is like, let us keep P fixed. Okay, so it is half comma half, and Q is, let's say, 1 by 4. Okay, so let me change P itself. Should I? Yeah, yeah. So let me take this 1 by 4 and 3 by 4, something like this. Okay. Now what will this be? This will be what? So first is half P log P by Q. So 1 by 2 by 1 by 4 will be 2, plus 1 by 2 log 1 by 2 over 3 by 4. So what will that be? So I think this will be 2 by 3, is it? Yeah, I think this is correct. So this will be what? So I'm just doing some calculation, okay? So this will be log 2. So I can do this thing, and minus 1 by 2 log 3. This is what it will be. And I don't know what log 3 is. I think it's 0.7 something, right? And if I'm not wrong, I think it is 0.7. And if it is 0.7 log 2, this thing, this is equal to 1, right? So 1 minus zero point 0.5, half of 0.7 is 0.35, and I think it's 0.65. Okay, so okay, now whatever this number comes, I might be wrong. Okay, like this is something that maybe check. Okay, I don't know, but I hope you can see that it won't be 0. Okay, and since it is not 0, you can see that in some sense it is telling P and Q are somewhat far away. They are not the same. If it was same, then you would have arrived at 0. So again, this is like so it is like an argument that I am presenting. It is not a formal justification, but nonetheless, I hope from this example you will agree that if P and Q are same, this term will always be equal to 1, and hence this log term will always be equal to 0, and hence this summation will be equal to 0. Okay, and if they are not equal, you will get some number which will be some positive number. And I mean, okay, let me write that down, that you know uh, so I mean, in some sense it won't be 0, and hence it will tell you that they are far away from each other. So there are some things to keep in mind about
Hello,
scale divergence.
hello,
Yeah, yeah,
Piyush.
yeah,
Yeah,
yeah, yeah.
maybe we should stop here today because actually there is some committee meeting here today in the shed, and they
Okay,
are saying that we need to close the shed.
okay, I see. Okay,
Yeah,
okay, so fine. Can you tell me like what time it would be better for tomorrow's session?
uh, anytime if you suggest, tomorrow we are all free. So like it is the last day today for here to commit for the committee for here to you know for the inspection and all.
Okay,
So like we'll be free by tomorrow.
okay, I see. So let me first stop the recording.
Yeah.